okay, while you're here. So yeah, let's continue with our class, uh, artificial intelligence for and machine learning for engineers. And we last time we were discussing about the uh, naive Bayes rule, and part of it is our discussion went back to the multi-hole problem, which is based on Bayes theorem, and we want to solve it on our own without any reference to any solutions from the internet, and we try to understand fully what it is about. Okay, so now let's discuss it again, and we hopefully will have a final solution, and then we will move on to finalize our discussion in the on naive Bayes rule, or yeah, naive, or just plain simply naive Bayes. Okay, so now I will share to you my screen. Okay, so this is the screen. So this is the one that we were trying to address. This is the one. Yeah, and we want to know whether we want to we want to switch the door or not. Okay, just for completeness, let's go back again. It will take time, but we need to do that so that we can Monty Hall problem. Where is the Monty Hall? Can somebody read it again, or maybe never mind? I don't want to. Labs, decision trees, base rule. Okay, there. Okay. So again, the problem is that we have three doors, and then two doors contain a goat and one door contain a car. And there's a guy, the host, Monty Hall, knows where the cars and the goats are. And then the person will try to choose, of course, to win the car. Okay. So once the person chooses one door, then it remains closed, and then the host will open one door for the player, and that, of course, that door has a goat. So now what is remaining is that two closed doors, one that was chosen by the player, and another, excuse me, and another one was not chosen. So the host will ask the player whether to change the initial choice or not. Okay. So will switching increase the probability of winning, or not switching will increase the probability of winning? So that's the question. To switch or not to switch? That is the question. Okay. So now we try to answer it using our own method from last meeting. This, I saved this one from last meeting. So now we say that we are just writing the Bayes theorem here. And so there are 6 events. Okay. One event, 3 events related to, is concerning about the car, the presence of the car in the corresponding door. So C1, if car is door 1, car in door 2, C2, C3, car in door 3. Okay, D1, D2, D3, door 1 is open. Oh, sorry, this is wrong. Door 1 is open, door 2 is open, the other one is door 3 is open. D3 is door 3 is open. Okay, so we just write the Bayes rule. Okay, so the problem is, given, we are just saying that given that door 2 is open, okay, what is the probability that the car is in C1? Okay, that is car in door 1. Okay, that's the question. So now let's go. I mean, we just rewrite the whole thing with respect to the Bayes rule. Okay, so based on Bayes rule, we write it P of D2 given C1 multiplied by C1, and then divided by the overall P of D, D, D2 given all the cases of D2. So that means that P of D2 given C1, probability of C1, plus P of D2 given C2, probability of C2, plus P of D2 C given C3, probability of C3. And what we are saying is that the second one is not possible. Okay? Probability of opening D2. Car door 2 is open. That's the event of D2. Okay? So car door 2 is open. Okay? The host won't open door 2 because car 2 is there. Okay? C2 is the event that car 2 is in door 2. So this is 0. So that one we agree. Okay? So now, the probability of C1, C2, and C3, yeah, that the car will be placed in in door 1, door 2, or door 3, when the game is just starting, yeah, all there's equal probability of putting the car. There's no restriction. Okay? So one third. There are three possibilities of putting the car in any of those doors. So each of those possibilities one third. Okay. So there is a trick here that I should mention to you that uh, the Bayes theorem is actually the right side of a Bayes theorem can be termed as something like a data or a known information. All known information is on the right side. Okay, that was the one that keeps us uh, confused last time. It's like a given data, and then this data is used to predict about a situation that is not that did not occur yet. Okay, so that means data, if we say that that is data, that is all the known information. Okay, to the right hand side, everything is known. Okay, so when you say everything is known, this is the case when this is the point of view of the host, because he is the one who knows everything. Okay. Okay, anyway. Okay, maybe it doesn't matter to you, but it does matter. So now, so all of these are one third. So this is one third. That's 0. So this one third, and this is one third. Okay. And then what is the probability of D2 being open given C1? Okay. Given that C1 is open, okay, now that will help us now. From the point of view of the host, okay? It will help us now. From the point of view of the host, he knows that the car is in C1. Okay? So if he knows that the car is in C1, so opening D2 is what? What's the probability of opening D2? So the car is in C1, the car is here. So how many, there's a nice car. Okay, how many, who is that guy? That's the rich guy always coming in social media saying he was rich and he was burned inside the car. Is that true? Very rich with many good, nice cars. Anyway, I keep on reading that. So, huh? A black guy, very rich. He's
Ginimbi.
Gininbi. What is he doing?
A trader.
He's a trader.
Let's see.
Okay, I wonder what he trades. Okay, anyway. Okay, so now here, so he knows that the car is in door 1. Yeah. So what is the probability of opening door 2? So that means there's only two possibilities for him. So it solves our problem before. Our problem was we are asking whether what if the guy chooses this one, he chooses door 1 or door 2. Then if the guy chooses C1, okay, then you only have one possibility of choosing C3. No, in that case, this is only about the known information. Okay, It is not about the other person. This is from the point of view of the host. It is a data. Okay, it doesn't need the information. It doesn't. There's no information about the choice of the door that was open. The choice of the door that was used, that was spoken, or that was chosen by the player. Okay, the choosing of the door is only in this side, on the left side of the equation. Okay. Okay. So in that case now, from the point of view of the host, if you're given C1 to be here, I mean, a car to be in door one, then opening C2, there's only two possibilities, either open C2 or open C3. So they have equal probabilities. So this probability is 1/2. Agree? Do you agree? There are two other doors only. You can either open this one or you open this one. Okay, those are only two possibilities from the point of view of the player. I mean, not from the point of view, sorry, from the point of view of the host. It can only open those two doors. So there's only two possibilities. Okay, that's 1/2. Next, what is probability? Okay, this one is 1/2. So again, so what is this? Given is the car is open, given that the car is in door 3, okay, what is supposed if the car is in door 3, okay? If this is the case, so what's the probability of opening C2? So again, it's 1/2, because if that is the case, there are two other possibilities now. It's either open C1 or C2. Okay, that's 1/2. Okay, so is this correct now? So this is 1/2 times 1/3 divided by 1/2 times 1/3. Maybe this is wrong. Plus 1/2 times 1/3. This is 1/2. This is wrong. Is that correct? That's 1/2, isn't it? Yeah, no? Is that 1/2? So because this is twice of 1/2 times 1/3, right? Yeah, it's 1/2. The denominator, that's twice of, and then you have 1/2 times 1/3 here. So they will cancel. So the possibility is 1/2. What's the answer? Hmm? What's the answer? What is C3? The car is in door 3, yeah?
Isn't it 0.5?
Hmm?
0.5, half.
Yes. So there's equal probabilities. No matter you change or not, it doesn't increase your chances of winning. That's what this one is saying.
are we expecting? What should we?
What? No, I don't know. I don't expect anything. We just solve it. I mean, we of course we will try to compare it with solutions, other people's solutions, but of course, based on our understanding, we'll try to solve it. Are we okay? If we are comfortable, are we comfortable with certain values? For example, let's go back. Okay, definitely this is not the same as the solution that we had last year. Okay, that's my point to you. Okay, I want to solve it the way, I don't want to say that my previous solution was correct. Yeah, but then maybe this is correct. Maybe it does not matter. Okay, but then here we say let's check the numbers. So is this correct? Probability of car placed in C1, C2, or C3 being 1/3? What do you think? That's correct? When we place the car in each of the doors here, when we place it, all of them have equal probabilities. I think it is correct. Okay, I think this is correct. Okay, then the probability if car if the car is in door one, okay, and then how many probability, what is the probability of opening door two? We have two possibilities. Come on. Is that true? Two possibilities. Given that the car is in door one, what's the probability of opening door two?
1/2.
Okay. We have two possibilities. Yeah.
Half.
Okay. So
Yeah.
probably this one is correct. So we agree that that one is correct. So we say yes.
Yes.
Okay, we agree. That's 1/2. Okay, this is okay. So this term is okay. You don't like yellow, you don't see it. This term is okay. Okay, so this term is okay. So this term is okay, this term is okay, this term is okay. So what is the term that we don't know is this one. Okay, let's go back to this term. Okay, it says here that it is car is in door 3. Yeah? And then the probability
Yes.
of opening door 2
The answer says still half.
is still half also.
Yeah. Because the host will never open the door that has a car behind.
Yes.
So you are left with two doors.
Yes. You are left with 2 doors. Yeah. So
Yeah.
1/2. Yeah?
Yes.
Who's that?
And I'm supposed to get points.
I'm so surprised. You're talking now. I should give you a medal, Mr. Musa. Not just points, I will give you a medal.
Okay.
Okay. Sorry. Okay. Okay, but the solution, okay, I will give you the solution. The solution that we used before, the value of that is 1. That is the one that makes a difference. Why is it 1? That's the question.
Because it depends on the choice of the player.
This is one. It's not 1/2.
Yes, sir.
Ah,
How is it supposed to be one? Sir?
yeah, that's why. It is one. It says it is one. Why? We need to understand.
Because it depends on the player's choice.
On the
Player's choice.
player's choice.
Whether yes, whether he chose C1 or C2.
Sorry?
It depends on the player's choice.